Welcome to the virtual classroom. Here in this class we will be seeing about various theoretical concepts related to IIR filter. So IIR stands for Infinite Impulse Response. The design of IIR filter is not similar to FIR because this involves infinite sample values. It is not possible to design with infinite sample values, and hence we go with the two-step process of design procedure, wherein which your step 1 involves with designing an analog filter. So here we can make use of two different techniques, either with Butterworth analog filter design or with Chebyshev analog filter design. Once it is being over, your step 2 is to convert the designed analog filter into a digital filter. So digital filter conversion can be done making use of impulse invariance transformation technique, bilinear transformation technique, matched set transform transformation technique, and approximation of derivative transformation techniques, and many more. So when we convert an analog filter into its equivalent digital filter, we are supposed to take care in order to maintain the stability of the filter. So in that, the analog domain, that is analog filter is in analog domain, that is represented by S plane, whereas a digital filter in digital domain is represented by a graph called as Z plane. So here the relationship between the two analog and digital frequencies have to be monitored carefully. So this is the pictorial representation for S plane and Z plane. So we were talking about stability, right? So the poles, what is pole actually? The denominator available in the transfer function is called as pole. So if suppose a filter is called as stable, all the poles should be located only in the left half of the S plane. So when we convert analog to digital filter, so all the poles from the left half of S plane should be carefully placed inside the unit circle of the Z plane. So this mapping have to be taken carefully. So this is one of the important derivation topic, derivation for impulse invariant transformation method. So basically there are three distinct formulas for impulse invariant transformation. So whenever you are being asked to write this question in theory, you can derive this, which we are going to see now. So this derivation is about how to find out the formula number 1. Okay, so let us start. Your H of S is called as analog transfer function or filter, and H of Z is called as digital transfer function or filter. So this is the basic process for making use of impulse invariant transformation. So let us start. H of T and H of N. What is the difference between these two? Both are called as impulse response, nothing different. But H of T is in continuous term signal, whereas H of N is discrete time signal. Okay, so how do you obtain H of N from H of T? By making sampling process you can obtain H of N. Both are impulse response, right? So while doing sampling process, you should consider Nyquist criteria. What is this Nyquist criteria? What happens, what is the benefit of using this Nyquist criteria? Aliasing is a problem, it is a drawback. Aliasing is nothing but overlapping of low frequency and high frequency components in frequency domain. So this process or drawback can be avoided if we make use of Nyquist criteria while doing the sampling process. What is this Nyquist criteria? Let me explain it. The maximum frequency present in H of T is called as F max. While you do sampling, the frequency for sampling should be greater than or equal to twice the maximum frequency of continuous time signal. So this is called as Nyquist criteria. So now we are having H of T in our hand. So when we take a transform called as Laplace transform, this Laplace transform is called as analog transform, which converts H of T from time domain to H of S in S domain. So this is the use of Laplace transform. So let us assume a transfer function with this standard format mentioned over here. So there is a numerator constant value and a denominator we have poles, right? So let us assume there are n number of poles, summation I is equal to 1 to n. This can be expanded like this. So here I would like to note you one thing, there is a formula in Laplace transform. If you take Laplace transform for e power minus at into u of t, you can obtain a format called as 1 by s plus a. So see this, this 1 by s plus a is the format available over here. So we have h of s, and if we take inverse Laplace transform for h of s, we can obtain h of t. So if we apply inverse Laplace transform for this particular format, this ai, for example this is ai, numerator constant term can be separated common. Okay, so this 1 divided by s plus pi can be represented as, instead of small a we have pi over here, so instead of e power minus at, you can represent it as e power minus pit into u of t. So now we have obtained with h of t. Okay, so what is the relationship between h of t and h of n? Once you do the sampling process, your h of t becomes h of n. So what is the representation of a sampling process? The term t can be replaced by n into t, where your capital T represents the sampling time interval. Okay, so wherever you have t over here can be replaced by small n into t, which converts your h of t from continuous time domain to discrete time domain. So now you can make note of a formula in Z transform, you have studied this before. E power minus at into u of n after Z transform can be replaced with a formula 1 divided by 1 minus e power minus at into Z power minus 1. So here we have h of n, here we have e power minus at into u of n format, and if we take Z transform for this, you can replace this format into this format, and this is the end of this derivation. So that your impulse invariant transformation can be, the first formula can be represented as, wherever you see 1 by s plus pi in the format of analog transfer function, you can directly convert it into 1 by 1 minus e power minus pi into t z power minus 1. So this is the end of first derivation of impulse invariance method. So let us see a comparison. Okay, so what is this? Analog poles and digital pole. What is the relationship between analog poles and digital poles? Analog means we talk about S domain, digital means we talk about Z domain. S is a parameter which is represented by the formula sigma plus j ohm. So this is called as real part and this is called as imaginary part, and this we call it as angular frequency. Similarly, Z is a parameter in digital domain which is represented by R into e power j omega. R is a real part and omega is the imaginary part. Omega is called as digital frequency, ohm is called as analog frequency. Okay, this is the term available in h of s in the denominator. So how do you find the poles of this transfer function? You just equate the denominator to 0 and calculate the value of s. Similarly, this is the denominator term for h of z transfer function. You equate the denominator term to 0 and just find the value of z. This gives the value of pole. So now we can compare the poles in analog domain and digital domain. So now the real part can be equated as, by comparing the real part in both S domain and Z domain and comparing the imaginary part in S domain and Z domain. Real part can be compared with this small relationship and the imaginary part can be related with this small relationship. Okay, so there are three different possible points to remember whenever you map a signal from S domain to Z domain. This may be asked as 4 mark or 6 mark question, even sometimes in 2 marks. So how do you map poles from S domain to Z domain? So there are three cases. When the poles are located in left side of S plane, it can be mapped inside the unit circle in Z plane. Similarly, whenever the poles are located in right side of the S plane, it can be placed outside the unit circle in Z plane. So when the poles are lying in the imaginary axis exactly, all those poles can be placed exactly at the circumference of this unit circle. So these are the 3 points to be remembered. If you see, so the relationship between analog and digital frequency, already we have seen this. So this is the relationship between analog and digital frequency. Digital frequency omega is equal to ohm into t and ohm is equal to omega by t. So this is the basic relationship. Okay, so this is one of the important derivation topic in IIR filter. For example, derive the basic relationship for bilinear transformation. What is bilinear transformation? This is one of the transformation technique which converts H of S, that means analog filter, into H of Z, that means digital filter. So while taking care of all those conversion, here also you can see the same kind of mapping techniques which we have already discussed in impulse invariant transformation technique. You just read out all those points mentioned over here. So next, so in order to derive the relationship between for a bilinear transformation technique, let us start with first order differential equation in analog system. So generally a first order differentiation equation can be represented like this. This is one of an example. Let us start with this. So for this equation, you are going to start up with integrating on both sides. So if we integrate this, here we have differentiation, right? So integration and differentiation gets cancelled with each other and you have limits over here. So how far this limits is being mentioned over here? Nt is the current timing, n minus 1 into t is the previous timing. So similarly the limits are applied over here also. Since this integration and differentiation gets cancelled, you are going to just apply the limits to y of t in this left hand side, whereas in your right hand side you can see x of t is a function and limits are there with integration. So here we can make note of a formula called as trapezoidal rule. So a trapezoidal rule says that a is the lower limit and b is the upper limit, f of x as a function of time. Okay, let it be. So if you suppose integrate this is a formula, right? B minus a divided by 2 into f of a plus f of b. B in the sense higher limit minus lower limit divided by 2. So this trapezoidal rule is applicable for this term in the right hand side slide. So this term, so 2 by t into 1 minus z inverse divided by 1 plus z inverse can replaced by a term called as S over here, and now the relationship is mentioned by the equation B. So now when you compare equation A and equation B, you can come across with this relationship as wherever you have S term, it can be just simply replaced by 2 by t into 1 minus z inverse by 1 plus z inverse. This is what the main formula useful in bilinear transformation technique, right? So this is the end of the derivation for bilinear transformation technique. So far we have seen two different derivations. Okay, so now this is a simple relationship. This may be asked in 2 mark. You just compare the relationship between analog and digital frequency by making use of bilinear transformation. I just simply justify. So when you want to compare the analog frequency in terms of digital frequency, this is what your relationship required. So at the end of this, you can come across two different representations. Analog frequency can be represented by this term, whereas your digital frequency can be represented by this term. Okay, so when you compare these two equations, you have been getting one idea in your mind. So what is that idea? So the relationship between the analog frequency and the digital frequency is not linear. It is non-linear with respect to each other. So this is what we are supposed to consider as an important factor, because we are designing IIR filter wherein which the stability of the filter plays an important role. Okay, so whenever you convert a filter from analog domain to digital domain, if suppose we have a linear relationship between both frequencies, stability might not play an active role. But since you have a non-linear relationship between analog and digital frequency, a problem, maybe this is called as a drawback actually. We call this process as warping effect. What is the effect of warping effect? We can see. So warping effect is a drawback which arises only due to the problem of non-linear relationship between analog and digital frequency, and due to which what happens, if you see, the conversion of poles from S plane to Z plane may not be linear as such we prefer. So these are the effects of pre-warping. Already I have told you, you can even have a readout of this particular topic. So if suppose I want to design a filter over here with these band of frequency, let me consider an example. Here I have 50 Hertz, here I have 200 Hertz, 250, 350, 500 and ending up with 1000 Hertz. For example, I am considering all these factors as filter cutoff frequencies in all these three bands. For example, due to the non-linear relationship between ohm and omega, what happens if you see, if you cross verify and expand all those points, if you see all these three bands are available as such we have given in the specifications of analog into digital. It is being converted. We have at the end point we have all the three bands, but you compare the width of all the three bands. So in the our specification lies with width 1, 2 and 3, but if you compare, these two widths are not equal. These two widths are not equal and ultimately these two widths are not equal. So because of this non-linear relationship, what happens when you design a band pass filter, it may end up with low pass or high pass filter. So this sort of problem we may arise. So this is called as instability. This is called as instability, and this called as warping effect. When you bend all those frequencies from analog domain to digital domain, it may look warped, and this is called as warping effect. And this relationship is for frequency response of the filter. Similarly, warping effect with respect to phase response is also being given. So when the phase response of a analog filter is being converted into a digital filter, and its corresponding phase response can be monitored as a straight line in analog domain is converted into a curved line in a digital domain. So this is what we call it as warping effect. Thank you.